Medical physics for you.
Hello everyone. Today we are going to continue the discussion about the interactions of ionizing radiation with matter. This lecture is about the interaction of heavy and charged particles with matter. In the previous lecture we have discussed the photon interaction with matter. Today we will discuss the interaction of other types of ionizing radiation like electron, alpha particle, proton, and neutron. And briefly see what type of interaction can happen when these types of radiation hit a matter. First, let's see what these particles are. The electron is the smallest charged particle in the atom. It has a negative charge. Sometimes it called beta particle. The proton is the positive charged particle that exists in the nucleus of the atom. Any element is distinguished by the number of protons in its nucleus. The number of protons called the atomic number. For stable atom, the number of protons inside the nucleus equals the number of electrons surrounding it. The neutron is a neutral particle that has no charge. It exists inside the nucleus like the protons. The total number of neutrons and protons called mass number. This is because the atom mass is concentrated in its nucleus as the electron mass is too small compared to other atom components. Alpha particle is 2 protons hand in hand with 2 neutrons. Sometimes it referred to as the nucleus of helium. Alpha particle has positive charge. The charged particles like electron, proton, and alpha particle interacts with the target atoms following the Coulomb force. This force increase as the charge increase and as the distance decrease. We will start with the famous charged particle in radiotherapy, the electron. Because its mass is too small compared to other atom components, electron considered as a light charged particle. Because of that, electrons suffer from multiple scattering and change in its direction when an electron beam falls in a matter. So, when electron hits a matter, like water or tissue, it loses its energy mainly through the excitation or ionization. In the excitation process, the transferred energy from the incident electron to the orbital electron is not enough to overcome the binding energy between the orbital electron and its atom, but can displace it from its stable position. The excited electron then returns to its stable position by emitting this acquired energy. In ionization, the transferred energy from the incident electron to the orbital electron is enough to overcome the binding energy and can dislodge the electron away from the atom. If the dislodged electron ejected from inner orbit, another electron from higher shell will fall into the hole and a characteristic X-ray is generated. This process called ionization because 2 ions are generated as a result of this interaction, the electron, with negative charge, and the rest of the atom, with a positive charge. The incident electron then is scattered with a kinetic energy that equals to the original kinetic energy of the incident energy minus the binding energy of the ejected electron and the kinetic energy of that ejected electron. Sometimes the ejected electron has enough energy to ionize additional atoms. Then it is referred to as a delta ray. When the incident electron beam has higher energy, it can find its way to come very close to the nucleus. In this case it interacts with the electromagnetic field of a nucleus and loses its energy by deceleration and deflection. This energy loss is transferred into Bremsstrahlung X-ray radiation. If we look at the dose variation of electron beam with depth, the following curve is obtained. The electron beam starts to transfer its energy via excitation and ionization directly when hits the surface, until it reached a depth where the maximum energy is transferred and absorbed. After that depth the transferred energy falls rapidly. As you can see in these curves, the dose does not reach to zero. That is because of the X-rays produced due to those electrons make interactions with the atom's nuclei and generate a Bremsstrahlung X-ray radiation. The amount of generated X-ray is proportional to the incident electron energy. That means by increasing the incident electron energy, the number of electrons that can reach the nucleus and produce X-ray increase. Losing energy per unit length called stopping power, or linear energy transfer. The stopping power is proportional to the square of the particle charge and inversely proportional to the square of its velocity. So, if we look at other particle, like alpha particle, which is the nucleus of the helium, consists of 2 protons and 2 neutrons, and compare it to beta particle, which is electron, we can see that the alpha particle beam can be fully stopped in a very short distance, while the beta particle can penetrate longer. For proton, where it is heavier than the electron but lighter if compared to alpha particle, its stopping power is somewhere between the electron and alpha particle. To imagine what happens when a heavy particle like alpha particle hits a matter, let's see what happens if there are bowling balls distributed randomly. Then another ball had thrown towards them. The incident ball will transfer large amount of its energy to the distributed balls and stop shortly. That is what happened with alpha particle. Because its high positive charge, plus 2 positive charges, and its heavy mass, the alpha particle has a high specific ionization. The linear energy transfer of alpha particle is high as it loses its energy rapidly. It is easy to shield against the alpha particles as a piece of paper can stop them. Alpha particle does not cause external hazard as it cannot penetrate the dead layer of skin on the surface of the body. But it can cause a potential internal risk. Because its high specific ionization, the weighting factor for alpha particle is 20. That means the consequences of tissue damage from alpha particles is 20 times compared to photons. Because it has a charge, proton interact with matter through the Coulomb force. The proton loses part of its kinetic energy due to inelastic collision with the atomic electrons cause either ionization or excitation. The proton beams scatter at significantly lower angles if compared to the electron beams. This is because they are larger and have more charges. As a result, proton beams have a more distinct lateral dispersion than electron or photon beams. The interaction of proton with atomic electrons is called multiple Coulomb scattering. Unlikely, a hard collision or nuclear interactions can happen. This nuclear interactions happen when the incident proton have enough energy to reach and interact with the atomic nucleus. The result of this interaction is an excited nucleus, and a secondary proton, neutron, or alpha particle is emitted. As it was mentioned few slides back, the stopping power is proportional to the square of particle charge and inversely proportional to its velocity. The rate of energy loss per unit travel length increases as the particle loses energy and slows down. So, the rate of energy loss reaches its maximum near the end of the particle's range as its velocity approaches zero. Because the proton scatters in a small angle, most of proton particles reach their maximum energy loss around the same depth. This curve shows the percentage depth dose curve for a monoenergetic proton beam. The peak at the end of the proton range called Bragg peak. Bragg peak also happens in electrons, but because of the electron beam suffers from multiple scatters in different directions, these multiple changes in direction during the slowing down process smear out the Bragg peak and make it not observed in the electron beam. This unique feature of proton makes it useful to be used in some clinical applications as we will discuss later in the proton treatment lecture. Neutron. Because they have no charge, neutrons, like photons, are interacting by indirect ionization. However, the neutron interaction with matter is different. Neutron interacts with matter either by scattering or absorption interactions. Scattering interaction is either elastic or inelastic interaction. The elastic scattering interaction is like a billiard ball collision, where the incident neutron interacts with the matter atomic nucleus. The recoil nucleus then loses its energy via excitation and ionization. In the large nuclei, the excited recoil nucleus loses its energy via releasing gamma rays. The transferred energy becomes very high if the target atom nucleus has same mass, i.e. hydrogen nucleus, as the incident neutron. While incident neutron lost small amount of energy when colliding with a heavier nucleus. That is why in bunker shielding design, when the linear accelerator generates 10 MV photon beam or higher, the hydrogenous materials like paraffin wax is used for neutron shielding because the lead, which is used for photon shielding, is not efficient in neutron shielding. Inelastic scattering is a type of scattering collision where kinetic energy is not conserved. The incident kinetic energy is greater than the kinetic energy of the nucleus and the scattered neutron, where some energy is acquired by the nucleus and becomes excited nucleus. Back to the stable state, the excited nucleus emits one or more gamma radiation. The inelastic collision is not common and most likely happen with high atomic number targets. Absorption means the incident neutron finds its way to be absorbed by the target nucleus. In this case, the incident neutron is fully absorbed by the target atom. That means the number of neutrons inside the atom nucleus increases. This interaction leads to the atom, or in other words the nucleus, become unstable. For this unstable nucleus to back to the stable state, it must do some kind of interaction and emits a particle like proton or alpha. If after particle emission the nucleus still in the excited state, it will also emit gamma radiation. In some cases, the nucleus emits only gamma radiation to back to the stable state, in this case this interaction called capture reaction. Fission. In the fission, the target nucleus gains enough energy to split into two new nuclei. So, for neutron interactions, it either by collision or absorption. The collision is elastic or inelastic. The absorption produce proton, alpha, gamma, or fission. Neutron shielding. Neutron shielding has 3 steps. 1. To slow down the incident neutron. 2. Absorb it. 3. Absorb the produced gamma rays. In radiotherapy, when 10 MeV or above is used in the treatment, there is a probability that neutron is produced. For most stable nuclei, the binding energy for the neutron is around 7 to 10 MeV. So, when photon energy is high enough, i.e. 10 MeV or higher, the photon might interact with the nucleus and produce neutron. So, it is important to take into consideration the neutron shielding if you are designing a bunker for linear accelerator that can generate photon beam with energy of 10 MeV or higher. Now, it is time for some questions. Question 1. What is the difference between the direct and indirect ionizing radiation? Give examples. Directly ionizing particles are charged particles that, while moving through a medium, can ionize atoms within it via electromagnetic force interactions. Examples: alpha, beta, and proton radiation. Indirectly ionizing particles are chargeless. They must interact with the medium to produce a charged particle, which then deposits energy through electromagnetic force interactions. Examples: gamma and neutron radiation. Question 2. True or false? A few inches of polyethylene can be added to the door to thermalize the neutrons and reduce the neutron dose for the linear accelerators produce 10 MeV photon beam. The above statement is true. The neutron contamination grows rapidly as the beam's energy increases above 10 MeV. Lower photon energy beams like 6 MeV fall below the energy threshold for photonuclear interactions. A maze configuration can significantly minimize the door's shielding requirements. With an appropriate maze design, the door is exposed primarily to multiple scattered radiation of significantly lower intensity and energy. In general, a longer maze, greater than 5 meter, can minimize neutron flux at the maze entrance. However, without a maze entranceway, a heavy door will be required to provide adequate shielding. Question 3. What is the Bragg peak? Bragg peak refers to the characteristic energy deposition pattern of charged particles as they travel through matter. In this phenomenon, at end of its path, the charged particle suffers from high energy transfer. This is because it reaches to its minimum velocity, so the stopping power at that point reach the maximum. The Bragg peak is clearly observed in the proton beam because the scattering angle of the proton is small, so the majority of proton beam deposit their maximum energy around the same point. That is all for today's lecture. Thank you.